Well, hello. Today we're going to be talking about octaves. Our objectives for today is in class we're going to build apparatuses that vibrate with certain frequencies. We're going to be able to explain the relationship between octave and frequency and describe the relationship of instruments and their corresponding frequencies and wavelengths. Okay, as we've said and stated up till now, we had given you the equation for the pendulum, and I believe just here recently in class we had talked about the one for a spring. But this right here is for our pendulum, and this would be the equation for the period of a spring apparatus. Sound and air. All right. Speed in air is related to the temperature, independent of the instrument. As we've discussed, sound travels faster in warmer air. So our equation is the velocity for air is 331 plus 0.6 times the temperature in degrees Celsius. So the question we have then is how fast will a wave travel in air at a temperature of 24 degrees Celsius? Well, the velocity would be 331, that's the constant, plus 0.6 times 24. So when we multiply this, we get 331 plus 14.4, which gives us a velocity of 345.4 meters per second. Let's get into talking about octaves. An octave, the interval between middle C and high C, that's 1 octave higher. An increase in pitch of 1 octave is doubling of the frequency. So the lowest note on the piano is an A with a frequency of 27.5 hertz. What is the frequency of the A 3 octaves higher? Well, if the lowest one is 27.5 hertz, the next one, right, 1 octave higher, is double that, and 27.5 times 2 would give us 55 hertz. 2 octaves, we'd have to double the 55 hertz. That would give us 110 hertz. A third octave higher would be doubling that again, which would give us 220 hertz. So when you hear someone saying they can go an octave higher, what that means is they are doubling the frequency at which they're singing at. Okay, this is a little bit of review from the previous day, but it says, what are the wavelengths of the 4 longest waves that can stand in a string 50 centimeters long? Well, if you remember, our first one was the string length, and I'm just going to say string length equals 1/2 of lambda. And that is because a stringed instrument has nodes at both ends because you pluck it and it vibrates up and down. Well, that would be half of the entire wavelength. So the first one here is the string length is 50, and it's half of the wavelength. How do we get rid of half? We multiply both sides by 2, and we get wavelength equals 100 centimeters, or 1 meter. The next one then would be 2 halves, or 1 wavelength. So we'd say 50 equals 2 over 2, or just 1 wavelength, and then that becomes wavelength is easiest, 50 centimeters. 50 equals 3 halves the wavelength, and we would multiply by 2 and divide by 3, and that gives us approximately 33.3 centimeters equals the wavelength. And then the last one is 50 equals 2 wavelengths. And that means we'd get 25 centimeters equals a wavelength. So here are our different wavelengths we have. Now what I want to go into here then again is showing us why. So here's our guitar. It is a really big guitar, and let's just put one string on it. It's the easiest to remember here, one string. And it gets out here, and here's where you tie it. And back here, well, let's go from here. Alright, here is our string. And if we pluck it, the half the wavelength is easy because it would be simply going down here. So that's not hard to understand. That would be, if we continued it, right, one wavelength would be over there because it has to finish. We have to stop where there are nodes. Likewise, I could compress it and I can get one full wave in here, and that's where we get the 2 over 2. I could extend it now. If I extend this, I can bring this part to here, and that'll give me 1, 2, 3 parts, or 3 halves of the wavelength. And then we can extend it to the next one, which gives us the 4 halves. So now that we've discussed that, let's go ahead and look into answering the bottom question here. What are the 4 lowest frequencies of 50 centimeter string if the speed of the wave is 340 meters per second? Well, we have learned that our wavelength equals velocity times the period. So what we're going to do is put these wavelengths in here. We're going to put this velocity in here and solve for these periods. My first one then is going to be 100. 340, solve for the period. The next one is going to be 50 equals 340, solve for the period. The next one will be 33 equals 340, solve for the period. And my last one would be 25 equals 340, solve for the period. Okay, what I've done is, one of the corrections I've found here, as I did the other day as well, this was 1 meter, 0.5 meters, 0.33 meters, and 0.25 meters. So I had to make those corrections first. My periods then, when I divided it, gave me 0.0029, 0.0014, 0.001 seconds, and 0.0007 seconds. And the frequencies then are just the inverses underneath. Here's your chance. What are the wavelengths of the 4 longest waves that can stand in a string 60 centimeters long? So, again, we're going to be talking about string lengths. You can set this up the exact same way as what we did on the previous. So if you want to rewind the video and watch it there and pause it, or you can set this up the bottom part here the exact same way as well, except your velocity is going to change, and then you'll be using the wavelengths that you calculate. Hey, I hope this is a good review for you. I'll see you on the flip side.